Now let's talk about the moment of force. Moment of force is defined as the measure of its tendency to cause a body to rotate about a specific point or axis. Now it is different from the tendency for a body to move or to translate in the direction of the force. Now in order for a moment to develop, the force must act upon the body in such a manner that the body would begin to twist or to rotate. This occurs every time a force is applied so that it does not pass through the centroid of the body or the axis of the body, and the moment is due to a force not having an equal and opposite directly along its line of action. Now, for example, in this picture, now if I apply a certain force here at point which has a distance r from the from the axis of rotation AB. Now the magnitude of the moment of force about this axis AB is the orthogonal component. So when you say orthogonal component, it's the component of this MO, which is parallel with the axis of rotation AB. So we are getting the orthogonal component along the axis AB, where O, the point O, is any point on AB. Also, the moment of force is equal to the force applied and then multiplied with the distance, or D, which is the perpendicular distance from A to the line of action of the force. Now imagine these two people pushing on a door at the doorknob from the opposite sides. Now if both of them are pushing with an equal force, then there will be an equilibrium. However, if one of them would suddenly jump back from the door, the push of the other person would no longer have any opposition and the door would swing away. Then the person who is still pushing on the door would create a moment, or it create a rotation or a movement on the door. The person who was still pushing on the door would create a moment on the door. Now in discussing how to calculate the moment of force about a point via scalar quantities, we will begin with the example of a force on a simple lever as shown here. Now in this simple lever, there is a force at the end of the lever which is a distance d away from the center. So this is the center, which is labeled A, and we apply the force which is d distance away from A. So this here on B. Then when using scalar quantities, the magnitude of the moment will be equal to the perpendicular. So M is equal to the perpendicular distance times the force. So again, D is the perpendicular distance. So between the line of action here is the line represented by the arrow here. So since the line of action and D are perpendicular, so that's what we're getting. Now to determine the sign of the moment, we determine what type of rotation the force would cause. So in this case, if we apply a force on B which is directed upwards, it will produce a counterclockwise rotation. So like this. Okay, while if we apply a force that is going downwards, it will produce a clockwise rotation. Now, a counterclockwise rotation would give a positive moment, so positive moment, but when it is clockwise rotation, it will cause a negative moment. Again, if it's counterclockwise, it's positive. If it's clockwise, it's negative. Again, I will emphasize that you have to remember that the value of D is the perpendicular distance from the force to the point we are taking the moment about. Now, earlier, this is the distance from the point where we are measuring the moment while we apply the force at this moment. So this is, we can call this r, but we are concerned with the distance that is perpendicular with F. So this is the perpendicular distance with the F. We're not concerned with this, with R. We are concerned with this D. Now we could measure the distance from point A to the head of the force vector, or the tail of the force vector, or really any point along the line of the action force, F. Now the distance we need to use for the scalar moment calculation would, however, is the shortest distance between the point of the line of action of force. So this is the line of action of force and this point A. This will always be a line perpendicular to the line of action of force going to the point we are taking the moment about. So for example, what is the moment of that force A exerts on point A, and then how about force B? Now let's focus first on force A. As you can see here, force A is directed downwards, and the distance from the point A, is 2 meters. And notice that this distance is perpendicular with force A. So we can just simply multiply. So moment A is equal to F times D, which is equal to 100 newtons times 2 meters. So this is equal to 200 Newton meter. But look at the direction. So as you can see here, if you apply a force of 100 newtons downwards, this will create a clockwise rotation. And we know that clockwise is negative, so let's put negative here. So the moment here is negative 200 Newton meter. For force B, okay, let's draw it first. So this is 2 meters. Okay, 2 meters. And then force is applied. So this is point A. Force is applied here, which is 30 degrees with this line, or D. Now this is 200 newtons. Again, to solve for MB, that is F times D. However, the D here is the shortest distance from A to the line of action, or to the line at which the force is applied. So there must be a perpendicular or a 90-degree angle between this D here and the line of action of the force. Now to get this D is equal to this 2 meters times the sine of 30 degrees. So here, this is the sine of 30. Note that sine is equal to opposite over hypotenuse. So the hypotenuse here is the 2 meters, while the opposite is D. So this is D over 2. So this is how we get sine theta. That's why we arrive in this equation. So MB is equal to 200 newtons times 2 meters sine 30 degrees. That is equal to 200 Newton meter. Note that if we apply a force that is directed towards in this direction, it will create a counterclockwise rotation. So therefore it's positive. So MB here is positive 200 Newton meter. Note that since MA is negative and MB is positive, so these two moments will cancel, and this rod here will remain at rest. Now in this example, given that T is equal to 28.3 kilonewtons, so this is 28.3 kilonewtons, and W is equal to 25 kilonewtons. 25 kilonewtons. Determine the magnitude and sense of the moments about the point B, okay, of the following force T. So you will get the moment caused by force T, force W, and the combined forces. Now, the best way to do this, since we're given with 20 meters from B to the point of T, and then point B, which is 16 meters, the distance of point B with the line of action of W, which is 16 meters, and the height of this. So 36, we have a total of 36 here, and then 36 here, vertical. Therefore, this whole triangle, the angle between this T and this horizontal is 45 degrees. And we can get the length of B using D is equal to square root of 36 square plus, okay, the distance here. So since we're looking for this, and then we are given with 36 and 16, so 16 square, that is 39.4 meters. So the length of B is 39.4. Okay, now given this 45 degrees and the length of this, and we are also given with 28.3 here. Now given this length here, which is 39.4, and the length here, which is 20 meters, plus the 45 degree angle here, we can get the angle here, which is, let's call this angle theta. Okay, so to find angle theta, it's the angle between this metal, I think, and this T. So we can use sine theta is equal to, but first let's divide sine theta with the angle, or with the side opposite to it, which is 20 meters. So sine 20 meters is equal to sine, okay, we know 45 degrees, and we also know the line that is opposite, or the side opposite that angle, which is 39.4 meters. So this gives us theta is equal to arc sine of 20 sine 45 degrees divided by 39.4 meters, which gives us theta is 21 degrees. Okay. Now to look for the moment caused by T, so let's redot this. So this is B, and this is the line of action of T. Okay, and this is angle theta, and this is the perpendicular distance, let's call this D, with this angle, with this line of action T. So this is T. Okay, so to get MT, so that is F times D, which is equal to F is 28.3 kilonewtons times 39.4 meters sine of 21 degrees. So that gives us 400 kilonewtons. So this is MT, and then meter. Now for MW, again, we can calculate this using F cross D, where D is the perpendicular distance with the line of action force, which is W. Now look, note that this is RD, and this is also already perpendicular with W. So we can just simply multiply. So that's 25 kilonewtons times 16 meters, which is equal to negative 400 kilonewtons. It's 400 since if we apply this force W, it will create clockwise rotation, so that's negative, while here if we apply force T, it will create a counterclockwise rotation. That's why it's positive. So this is MW. Now, so the third one is the forces combined. So we will just combine the total, the MT total is equal to, so MT plus MW, which is, so we have positive 400 and negative 400s, it's 0 kilonewton meter. Sorry, we have meter here. Okay, so which means this system will remain in equilibrium, or it will not rotate. The next thing that we will discuss is a couple, and a couple is a special case of moments which consist of two parallel non-collinear forces that are equal in magnitude and opposite in direction. So for example here, if we apply a certain force at this point towards this direction, while this we apply another force that is opposite and has the same magnitude with the first force that is directed towards in this direction, this is what we call a couple. For example, the forces that two hands apply to turn a steering wheel are often a couple. Let's say for example, if here I apply certain force towards this direction, and at this point I apply another force that is opposite but equal in magnitude, so it will let the steering wheel to rotate at a counterclockwise rotation. Now if I apply a force that is directed here while another force is here, then it will move in a clockwise rotation. Now if the forces applied by two hands are unequal or not equal, there would again be an unbalanced force creating the translation of the system. However, we cannot consider that as pure couple, since couple always consists of two forces with equal magnitude. So for us to calculate the moment of couple about point using scalar calculations, so for example here we have to add the couple or the moment of couple caused by each force. So for example, so here the first moment is caused by force, this force multiplied with the distance from this point O, so that's A plus D, and then that causes a positive moment since it causes a rotation of counterclockwise. While this force again will create a moment that is negative since it will create a counterclockwise moment. So that is F times the A, which is the distance from the point of application and this point of rotation. Now here is an example of a common street lamp. Now the lamp creates a magnitude, or creates a moment with a magnitude determined by the weight of the lamp here, so here, and the moment arm D. So this is the D. Now this moment is resisted by a couple generated by the tubes supporting the arm. The two forces of the couple can be seen here, and it shows. So at the bottom there is a compression, and at the top there will be a tension here. Now here's an example problem. We have here two couples that act on the beam in which D here is equal to 8 feet, and we are asked to find the resultant couple. Now in order to do this easily, let's get the components of the different forces first. These are the components of this vector. Now these two are couples, so both of these are 60-pound forces. We can get also the components of this. Now let's get the component of the 60-pound force first. So let's get F1x. So this is the x component of this force. So this is equal to 60 pounds multiplied with, since we are getting the x component, we will multiply it with the ratio of the x component with the horizontal. So as you can see here, we have 3 for the horizontal and 4 for the vertical. So that's 3 over 5, since this is the ratio of the x component with the resultant, okay, or the hypotenuse here, which is 5. So this gives us 36 pounds, okay, which is to the left, okay. And now for the F1y, so that's 60 pounds multiplied with the ratio of the vertical component with the hypotenuse, which is 5. So that's 4 over 5, so which is equal to 48 pounds, going up. So similarly, we will get also the components of these vectors or these forces. Now for this, we have, let's label it F2x, so that is 40 pounds. Okay, so since we are given with this angle, since we're getting the x component, this is an adjacent side with this angle 30, so we can use cosine. So since cosine is adjacent over hypotenuse, so that's cosine 30 degrees, which is going to the left. Okay, and then F2y, so that's 40 pounds, and then this time I'm getting the opposite side here. Okay, since I'm getting the opposite side and hypotenuse is sine, opposite over hypotenuse, so sine of 30 degrees going up. Now we are going to look for the moment. Okay, for M1, it's equal to M1x, meaning I'll just consider here the moment produced by the x component plus M1y, which is the moment produced by the y component of this force. So M1x is 60. So again, in getting an M, it's equal to the F times the perpendicular distance. Now force, so for M1, so that is 36 pounds. And then here, since we are dealing with couples, we are getting the distance between the two coupled forces, but since they are lying on the same line here, it seems that they have no vertical separation, so the separation distance is 0. That's why this term will become 0 later. And then now for the M1y, so that's 48 pounds. The separation distance that is perpendicular with this force is this 4 feet, right? So since they are separated 4 feet apart, we can get, or we can put here 4 feet as the separation distance. It's important for us to consider the direction of rotation. It can be clockwise or counterclockwise. But for this, again, we're dealing with the y component. So we're just looking at the y component. So this is going down and this is going up. And it can produce a clockwise rotation. So this is clockwise rotation, and clockwise rotation is negative. So that's why we put a negative sign here. Therefore, M1 is equal to, so this becomes 0, 192.0 pound feet. Now let's look for m2. So similarly, m2 is m2x plus m2y. So now m2x, we will look at f2x here. So is 40 pound cosine 30 left. So this is 40 pounds and then cosine 30 degrees. Now since we are dealing with the x component here of this force and this force, we will get the perpendicular separation distance. So the perpendicular separation distance is this, which is equal to 8 feet. So that's 8 feet. Now let's consider the effect of these forces on the rotation of this. So it can cause a clockwise rotation. That's why it's positive. Now plus, okay, now let's look at the y component of m2. We will use this y components of the force. So it's 40 pounds. So I'll just write it here, 40 pounds, and then sine 30 degrees. So now we will get the perpendicular separation distance between the two. Again, since they are lying on the same line here, it seems that they don't have an x component separation, which gives us a 0 for this value or for this term, and that is equal to 277.1 pounds feet. Now for the total, we have m is equal to, or summation of m is equal to m1 plus m2. So m1 is equal to negative 192.0, and then m2 is 277.1 pounds feet. So this is equal to 85.1 pound. Okay, so this is summation of m. Is the final answer.